Hello friends, today we are discussing the protection of privilege levels for the part 5 of the microprocessor subject, protection and privilege levels. With in a previous level sub lectures we'll see how the Colgate works. Okay, with the Colgates there are four privilege levels are used to check the validity of the control transfer via the Colgates. CPL, current privilege level, RPL, restricted privilege levels, DPL of the get descriptor, DPL of the get descriptor level, DPL of the descriptor of the target segment. These are the four privilege levels are used for checking the validity of the control transfer via the call gate. How the control is transferred via the call gate, depending on that, these are the four privilege levels are there. Only the call instruction can use the gates to transfer the smaller privilege level. So the call instructions are used to transfer the smaller privilege levels from one gate to the another gate. For jump instruction, the privilege rules are maximum for the jump instruction if the CPL current privilege levels and a restricted privilege levels. Both maximum of these both will be less than get of the DPL value. If the maximum of the CPL and DPL values are given, or we have a current privilege level or a restricted privilege levels, maximum of both these values, if the less this value is less than of the DPL value, in that case only the jump instruction is executed and according to the privilege rules. If a target segment DPL is equal to CPL, if a DPL is equal to CPL, in that case the jump instructions are executed. For a call instructions, the rules are okay. The maximum value of the CPL, that is the current privilege level and a protected privilege level, if which is less than a get descriptor privilege levels. A target segment value, a DPL is less than equals to the CPL. Okay, see here. Yeah, for the jump instruction, target segment DPL is equal to the CPL, whereas in case of the call instructions, a target segment value DPL must be the less than the CPL value. So while calculating the values, the maximum of the CPL and the RPL, that is the current privilege level and a protected privilege level, restricted privilege levels. Okay, in which in both of the instruction jump and the call instructions, both the values are compared. If the values are less than the get DPL values, in that case, if the target segment DPL is equal to CPL, only in that case the jump instructions are executed here, and if the target value DPL is less than the CPL value, in that case the call instructions are executed. A privilege check via the call gate. As we know that a code segment is there in which the CPL value, current privilege level value is there. This value is given to the CPU for the privilege check. Also, the RPL, that is the requester privilege value in a target selector, which is also given, to the privilege check by the CPU. A descriptor get descriptor is there. Okay. You know the DPR descriptor privilege level. DPL value is given to the privilege check by the CPU, and a executable segment descriptors is there in which a DPL value descriptor privilege level is there. These values are given to the privilege check for a privilege check via the gates. These values are checked in us by the CPU according to the if the CPL and DPL values are CPL and RPL values are less than or compare then with a CPL values, then only the jump and call instructions are executed for privilege checking via the call gates. Task switching. Task switching checks that the current task is allowed to switch to the designated task. Task switching is a concept which checks that the current task is allowed to switch to the designated task if the DPL of the TSS descriptor is less than of the maximum of the RPL of the gate and at CPL. RPL stands for restricted privilege level and CPL current privilege level. If the values of the both the one of the means both the values are compared and maximum value is being considered, and if this maximum value of this one of the register RPL and the CPL is less than the TSS descriptor, then only the a task is allowed to switch to the designated task. Checking that the TSS descriptor of the new task is marked present and has a valid limit. uh, TSS switching, in which it will check that the TSS descriptor of the new task is marked present and has a valid limit. If it has a valid limit, the saving the state of the current task. Loading a TSS task switching loads the task register with a selector of the incoming task TSS descriptors, marking the incoming task, a TSS descriptors as a busy and setting the TS task switch bit of a MSW. Loading the incoming task states from its TSS task state segments and resuming the execution. Means a incoming task state TSS is loaded and it will resume the execution. So a task switching is done depending on the values of the RPL and the CPL, and while loading the task, a TSS resuming the execution, a task switch bit of the MSB. By marking the incoming TSS descriptors are busy and setting the task bit of the, after setting the task bit, the task switching will be done to the designated task. Every task switch sets a TS task switch bit in a MSW machine status word. Is every task switch which sets the task TS bit, that is a task switch bit in a machine status word. A new task begins executing at the privilege level indicated by the RPL of the CS selector value that is loaded in from the TSSR. Every task switch sets a task switch bit in a machine status word, that is a MSW. Means wherever the task switching is there, task bit is set in a machine status word. A new task begin executing at a privilege level indicated by the requested privilege level of a code segment selector value which is loaded in a TSS. Task linking, how the tasks are linked while switching from one task to the another task. The black backlink field of a TSS and the empty nested task bit of the flag were together allow the 8036 to automatically return to the task that is called another task or was interrupted by another task. In call instruction is used here. Okay, a backlink field of a TSS and a nested task bit of the flag word register together means a TSS and a flag bit of a nested task will together allow the thread 6 to automatically return to the task that is called another task or was interrupted by the another task. Means a thread 6 can automatically switch over from one task to another task by the backlink field of the TSS and a nested task bit of the flag bits whenever the call instruction is executed. The empty flag bit indicates whether the check backlink field is valid. What is the importance of the empty field? It will indicate whether the backlink field is valid or invalid. If the empty is set, that thread 6 switches back to the task selected by the backlink field. If the empty bit is set, a thread 6 processor switches back to the task selected by the backlink field. A busy bit prevents loops. When switching to the task, a processor automatically sets a busy bit of a new task. Whenever a processor switch from one task to another task by the task switch methodologies, it will switch a busy bit. It will set a busy bit of a new task. When switching from the task, the processor automatically clears the busy bit of the old task if that task is not to be placed on a backlink chain. While Switching from one task to another task, a processor automatically clear up the busy bit of a previous task which is not placed on a backlink chain. If the task is placed on a backlink chain, its busy bit remains set. Means if the task is placed on a backlink chain, its busy bits are remain set. If the task bit is not placed on a busy backlink chain, its busy bits are cleared up by the processor itself. When the switching to the task, the processor signals an exception of the busy bit of a new task is already set. When switching to the task, the processor signals an exception. Okay, while switching from one task to another task, the processor signals an exception if the busy bit of a new task is already set. Means if a busy bit is already set while switching from the task, a processor signals an exception in such a cases where a busy bit is already set and a processor switching the task. In that case, it signals an exception. The LDT selector and PDTR fields of the TSS gives the software system designer flexibility in utilization of the segment and a page mapping features of the 80386. A task address page in which a LDT local descriptor table selector and a PDBR field of the TSS gives the software system designers flexibility in utilization of a segment and a page mapping feature of 80386. A task linear to the physical space mapping. How the task linear physical space mapping is done. Here the TSS is given there a PDBR bit, which is a page descriptors. A PD bit is there, a page table is there in which the page table entry is there, which goes to the page table entries or goes to the page frame. That is a task 1, task 2, task 3. Okay, task A page, task each page of the task. So the PDE entries are goes to the PTE entries, and these PTE entries can share with pages. Okay. Task B TSS, which has the PDBR field, which access the PDE, and through that PDE, it access the PTE entries to access the task A, task B. Okay, page frames are there which are used to access the task through the task gates. A task logical address space to share a data. Task must always have a common logical to linear space mapping. Okay. While sharing the data, task must have a common logical to linear space mapping. That is, they must also has access to descriptors that points into the shared linear address space via the GDT, means global descriptor table. By sharing the local descriptor tables, two or more tasks can use the same LDT if the LDT selectors in their TSS select the same LDT segments. By descriptor analysis in a LDT, by sharing the LDTs by the local descriptor tables. Thank you friends for watching the video.